Our next speaker is Alexandre Martin, and he will, from Heriot-Watt, and he will talk about cubulating Artin groups via cubical small cancellation theory.
Thanks a lot, and thanks to the organizers for the invitation. It's great to be back. Actually, I just checked what I was talking about last time at the previous NPC workshop, and it turns out I was talking about some groups acting on cat-zero cube complexes in presence of small cancellations. So a lot has changed in 8 years, but there are some themes that are kind of coming back cyclically. So today I'm going to be talking about some joint work with Macarena Arenas on the geometry of Artin groups, and specifically on how to cubulate some of them. So I'm going to start with the definition of Artin groups. We've seen RAGs last week and general Coxeter groups, but I don't think we saw general Artin groups. So to define an Artin group, we need some data encoded in a graph, a presentation graph. So a presentation graph is a finite simplicial graph, so no loops and no double edges, which we're going to denote gamma, such that every edge has a label. So let's say I have an edge between two vertices denoted A and B. I've got a label MAB, which is an integer at least 2. And out of this data I can define some groups. So I can define the Artin group associated to gamma. So A gamma, which is given by the following presentation. So I'm going to put one generator for every vertex of the group. So the generating set is the vertex set of gamma. And whenever I see an edge between two vertices A and B, I'm going to add a relation of the form. So the alternating word ABAB, etc., is equal to BABA, etc., where the length, so I've got exactly MAB, so that label, on both sides. And that's for every edge between A, B, and label MAB contained in gamma. And there's another group that maybe people are more familiar with that we can define, which is the Coxeter group, denoted W gamma. Same generating set and similar relations, so same as above, but we also require that every generator now becomes an involution, so an element of order 2. So A square is the identity for every generator. So let's maybe give some examples. So we start with like the most basic one, maybe not the most interesting one. If gamma is a discrete graph, so no edges. So I've got a bunch of generators, and because I've got no edge, I've got no relation, so I just get a free group. A gamma is the free group on number of generators as rank. A family that has been extensively studied is when all the labels are equal to 2. So that's the family of right-angled Artin groups. So I've got a bunch of generators, and my relations are of the form, some of them commute, and that's it. So that's what we call a right-angled Artin group, and similarly we've got a right-angled Coxeter group. And maybe to give an example that is not right-angled, let's say gamma is the following graph, so a triangle, with labels, let's say ABC, 3, 3, 2. So that's quite a famous Artin group. So A gamma in that case is isomorphic to the braid group B4 on 4 strands, and the corresponding Coxeter group is the symmetric group S4. And more generally, every braid group can be represented as some Artin group for a slightly more complicated graph. Maybe some Artin people or Coxeter people in the room are more familiar with the presentation given by the Coxeter diagram or the Dynkin diagram, which is a slightly different one where we don't put edges when there's a label 2 and we do put edges when there's a label infinity. But we're going to be using the presentation graph, which from a geometric perspective is often maybe more relevant in that they appear as links in certain complexes associated to these groups. Okay, so Artin groups in general are kind of a wide family that generalize rags, but also braid groups. And so we'd like to understand them, and at the moment, in general, we don't. So essentially, any property about groups that you're interested in is unknown for general Artin groups. There's a lot has been done for certain subfamilies that have a richer combinatorial structure and some nicer actions on non-positively curved complexes. But in general, we still don't know, for instance, we still don't know the word problem for Artin groups. Even though this is a very nice presentation, quite close to Coxeter groups for which this is known, we don't know the word problem. We don't know whether these groups are torsion-free, even though we expect they are. We don't know the center of these groups. We don't know whether they have a finite classifying space. That's kind of essentially the K-pi1 conjecture, which is maybe the most famous problem in that subfield. So really, a lot, well, very little is known. And on the geometric side, since this is a non-positively curved conference, on the geometric side, essentially we expect Artin groups to be as nice, or sometimes even nicer, than Coxeter groups. And the geometry of Coxeter groups is reasonably well understood. So in particular, we expect, or at least it's conjectured, that Artin groups should be cat0. There are people who wonder whether they might be all hierarchically hyperbolic. So what do we know? So for instance, in general, Artin groups are not hyperbolic unless they're free groups. That's the only case, because as soon as you have an edge, you contain z squared. So they're not hyperbolic. In general, they're not relatively hyperbolic if they're not obviously a free product. That follows, for instance, from thickness due to Berstock, Drutu, and Mosher. So there are a few results that have been obtained. For instance, Thomas et al. Proved that if the labels are sufficiently large, your Artin group is cat0. There's some work, joint work of Alessandro Sisto, Mark Hagen, and myself, where we proved that some Artin groups are hierarchically hyperbolic. Yes, hierarchically hyperbolic, but we're very far from a kind of a general understanding of the geometry of these groups. So the type of structure I'm going to be interested in today is cubulation. So proper cubulation, so proper action on cat0 cube complexes. Proper, so metrically proper actions on cat0 cube complexes. So having a proper action on a cat0 cube complex implies a lot of things, especially if you have like more than just a proper action. Hagerup, for instance, in particular, Baum-Cohn. If, for instance, there's a result of Stagiev and Wise that if G acts so properly on a finite dimensional cat0 cube complex, so CCC, then G satisfies the Tietz alternative, which is something you would expect from non-positively curved groups. And a slightly stronger or like more geometric Tietz alternative, namely, if you have a finitely generated subgroup, it either contains F2 or it's virtually abelian. So not just virtually solvable, but virtually abelian. If you have even another type of very nice action on the cat0 cube complex is virtual specialness. It's a result of Haglund and Wise that if G is virtually special, so I'm not going to define what it means, but it's a very specific type of action on a cat0 cube complex. Then, in particular, G virtually embeds in a right-angled Artin group, which has a lot of applications. So it's linear over Z, so it's embedded in some SLN Z. So it implies, in particular, residual finiteness. Virtual torsion freeness. And all this are properties that we don't know about Artin groups in general. Like even residual finiteness is unknown in general. Actually, residual finiteness, even for the subfamilies of Artin groups where a lot more is understood, like two-dimensional Artin groups, where the K-pi1 conjecture has been proved, there's a very nice cat0 space on which they act. We still don't know that they are residually finite in general. I think Kasia Jankiewicz has some results about certain two-dimensional Artin groups, but in general it's unknown. So constructing these actions on cat0 cube complexes can help you, unveil some of that structure, and so that's what we'd like to do. So let's maybe start. I mentioned that we expect Artin groups to be as nice as Coxeter groups. So what is known for Coxeter groups? So there was a result of Niblo and Reeves that Coxeter groups are properly cubulated. And then Adlund and Wise proved that they're actually virtually special. So it's quite natural when you know this for Coxeter groups to wonder whether the same might hold for all Artin groups. So two questions the main question I want to focus on today is, okay, so are Artin groups properly cubulated, but I'm maybe going to phrase it as which Artin groups are properly cubulated. And then you can even ask, or virtually special, / virtually special. But I'm only going to focus on the cubulation today. Yes, the virtually specialness was asked in that paper by Aglund and Wise. And I think just the proper cubulation appears in a list of problems by Charney, but I actually don't know if it was asked before, but at least it appears in that list of problems about Artin groups. So what was known about cubulations of Artin groups? So there were some results, not many. So for instance, maybe since I mentioned rags as an example, we know that rags are even co-compactly cubulated. Namely, there's just to mention there's that geometric action on the Salvetti complex for these groups. Particular Artin groups I'm going to mention quite a lot in this talk because they are going to be in a sense building blocks for us. Are what we call dihedral Artin groups, so Artin groups on two generators. So with that notation, that would be Artin group on a single edge with label M, so something of this form, AB, and then ABA equals BAB, etc., with length M on both sides. So those ones are actually virtually isomorphic, so their structure is well understood. They're virtually isomorphic to Z cross a free group, so their central quotient is a virtually free group. So in particular, they are co-compactly cubulated, and they act on a product of a line and a finite valence tree. What else? So I've been focusing so far on co-compact cubulation, so maybe as the first question you might wonder, are maybe Artin groups co-compactly cubulated in general, or virtually co-compactly cubulated? And essentially, no. So in general, Artin groups are not co-compactly or even virtually cubulated. For instance, this is a result of Thomas et al. So braid groups are not virtually co-compactly cubulated for n, so Bn, for n at least 4. So even that small triangular Artin group I mentioned earlier is not co-compactly cubulated. To give you another example, so there was work of et al. And independently Jingyong, Yankiewicz, and Piotr Trzytycki. For instance, just to give an example of something that is dimension 2, so if all label, let's say that gamma is connected. So connected is not really an essential assumption. If it's not connected, you have a free product, and co-compact cubulation or any sort of cubulation behaves really well with free products. So connected, but all labels are odd. So this forces your Artin group to be what's called large type. So in particular, it's cohomological dimension 2. And they prove that A gamma is co-compactly cubulated if and only if gamma is a single vertex or a single edge. So as long as you have more than 2 generators, you cannot be co-compactly cubulated in the odd label case. If you allow some even labels, a bit more can happen. So there's actually a conjectural classification by Thomas et al. Of exactly when your Artin group is compactly cubulated, which is a bit hard to state, which is why I don't want to do it. But really, the idea is, like in general, your Artin group is not going to be compactly cubulated. However, it might still be that they are properly cubulated. That would still be nice. So what about proper cubulations? So there were some results by, again, Thomas et al. So some results by et al. For what's called triangle-free, for some triangle-free Artin groups, not all of them, where you construct an explicit proper cubulation. But apart from that, not many examples are known. So to give you an idea of how far we are from understanding proper cubulation, here's something that is still open. Is the braid group B4 properly cubulated? That is still unknown. So B3 is an example, is a dihedral Artin group for the label 3. So that one is properly and even co-compactly cubulated. But from n at least 4, nothing is known. Okay, so let's done some slightly weird board movement here, but okay. So let's state the main result that I'm going to be talking about today. So the main theorem, part 1. I'm gonna give a slightly simplified version for now, and then at the end I will give slightly more cases. So with and then itself. So f all labels satisfy. So all labels are at least 8. Then A gamma. So it's properly cubulated, but acts properly on a finite dimensional Cat0 cube complex. So all labels at least 3 was large type, so this is referred to as the class of XXXXXL Artin groups, but where all labels at least 8 will work for today. And so what I would like to do is to give you an idea of how we prove such a result. And so ideas of small cancellations are going to enter the picture. So how do we prove that something is properly cubulated? So I'm going to be talking about a kind of a standard. By the way, do we see that bit if it's that high? Yeah. Okay. So I'm going to talk about a very fruitful and standard method now to prove cubulation, which is to construct a whole space structure. So whole spaces. So whole spaces originated in the work of Zagiev on codimension 1 subgroups, and then was generalized by whole spaces kind of were introduced separately by Agoun and Paulin. Was also the work of Zagiev on codimension 1 subgroups, and then the connection between whole spaces and Cat0 cube complexes was formalized by both Nika and Chatterjee and Niblo. So I'm going to define a whole space, but I'm going to define a slightly more restrictive notion of a whole space, which is actually the one we will going to need here. So definition. So let's say that X is a connected graph. A wall of X. So, yeah. A wall of X is a set, say W, of edges of X such that if you remove the set of midpoints of these edges for E and W, this subspace has exactly 2 connected components. So generally a whole space is defined as a whole space structure is defined as a set of partitions of a certain set with some extra conditions, but in practice a lot of the time we're working with sets that are concrete graphs or concrete complexes, and the way we construct walls are really by looking at the complement of some subspace. And so a whole space structure is a whole space structure on X is a collection of walls of X. So maybe let's give some concrete examples where, let's say, if what is kind of the prime example of this, if you have your favorite Cat0 cube complex, let's say the cube like this. Then there's the notion of hyperplane of that cube. That bunch of hyperplanes. Okay, I'm just gonna draw a few. Okay, I've got this one here, which is a bit more substantial.
Blue is almost invisible.
Okay, green.
Yeah, that's good.
Okay, thank you. Okay, and if I remove, okay, maybe I should say the one skeleton of this, and if I remove the midpoints of the edges here, I separate my my one skeleton into two components, above the green hyperplane and below the green hyperplane. But naturally, there was a result of Sagiev that if you just forget about the cube complex and you just look at the poset structure of, well, not the walls, but the complements of these walls and their poset of inclusion, you can reconstruct completely the cat zero cube complex. So these hyperplanes really encode a lot of the structure of the complex. And the idea was, well, walls kind of separating a complex in two bits is something that you can do in a lot of complexes that are not cubical in nature. And out of this, you can construct an action on a cat zero cube complex. So it's a theorem. So maybe let me started with the work of Sagiev, and then the real formalization is due to Nika, that if you have an action of on a graph with a wall space structure, then out of this you can construct an action of G on what's called the dual cat zero cube complex. Let's maybe give it a name for later if I have a wall space structure W. Okay, so it's kind of theorem with square quotes here because, well, if I don't tell you how you construct that cat zero cube complex, you can't really say much. But this is essentially a recipe for constructing out of a wall space structure an action on the cat zero cube complex. Now, of course, the properties of the action are going to depend on how nice your wall space structure was in the first place. So I'm not going to detail that construction, but I'm going to give you a couple of examples to see what can happen, and we're going to use these examples when we move to Artin groups. So let's have a look at some examples and how walls are constructed. I'm just going to do two examples. Let's say first X is so the standard calligraph of Z square, so a square grid. So you can think of it as a cat zero square complex, and if you take the family of hyperplanes, that's what I said earlier, you will reconstruct the original action. So I'm going to do something slightly different. I'm just going to take the family of walls coming from the vertical hyperplanes. And if you do this with an action of Z square on it, if you do this, the cat zero cube complex with the associated action of Z square on it is going to be an action on the real line, but with Z stabilizers everywhere, etc. So in particular, it's an action that is co-compact, but not proper. And let's look at another quick example, which is, so you start, let's say, you start from, okay, let's try to draw this. The tiling of the Euclidean plane by equilateral triangles. reasonable. So the dual graph of this, you can think of it as the Cayley graph of the Coxeter group corresponding to the triangle 333. So here, this is the Cayley graph of the Coxeter group 333, etc. So that's the tiling, the regular tiling by hexagon. And these original, like these three sets of lines that define the tiling, they define a wall space structure on that Cayley graph. And for this, if you take the dual action, what you get is an action of that Coxeter group, but on R cube with its standard cubulation. In particular, this one is with the plane kind of embedded as a transverse copy. And this one is proper, but not co-compact, even though the original action was geometric. So the properties of the action on the dual cube complex don't always reflect the original properties that you started from, so you have to be a bit careful here. Let's have a look at a final example that is going to be a sort of inspiration for our work, Coxeter group, which is related to Wise's work on small cancellation groups. Okay, by the way, are there questions so far? So let's have a look at the following example. That's going to be kind of a red thread for this. So let's say my group is the Coxeter group, but for the triangle 444. Whose Cayley graph is kind of looks a bit, well, just very closely looks a bit like this. It corresponds again to a tiling, but this time it's a tiling of the hyperbolic plane by octagons. That's the Cayley graph of G. So, you can think of not just the Cayley graph, but the Cayley complex if you add those cells. So those cells encode the relation. For instance, if I have A, B, C here, I'm going to see AB equals to BA, BA, etc. I'm going to see the three relations on those three main cells. So this presentation complex has a particularly nice geometry because it has what's called a, okay, so I'm not going to define C prime 1 over 6 in sort of combinatorial way, but it has a C prime 1 over 6 small cancellation geometry in the following sense. For any P and P prime polygons, so cells of this presentation complex, these cells are going to have a very small overlap, or a relatively small overlap in the following cells. You can see it on that picture. These two octagons intersect in exactly one edge, and that's the only thing that can happen. Either they're disjoint or they intersect at, say, well, actually no, in that case it's really one edge. But in particular, the intersection for the combinatorial length is strictly less than 1 over 6 the number of edges on either of them. So that's a small cancellation sort of condition, and using this idea or this geometry, Wise was able to prove that so finitely generated C prime 1 over 6 groups are actually co-compact free, but cubulated. And how did he do that? So the key idea was to construct a wall space structure and then understanding enough of the action to prove that the action on the dual is proper and co-compact. But the key idea is to extend walls on the cells. So here my cell is 1 octagon. So I can, for instance, I'm going to take as a wall the diameter, and I've got many ways of doing this, for instance this or this, etc., into walls of the wall of the calligraph. So the picture here would be, for instance, I've got this wall of that particular cell, and then I'm going to keep extending by going to the opposite edge, which in that case is that one, etc., etc. And so the key thing, this is actually quite a difficult result because you need to make sure that you're not going to, when you extend this way, you're not going to have like self-intersection if, or that this is indeed two-ended, or you don't loop on yourself. And so this C prime 1/6 small cancellation geometry is a sort of geometry that allows you to get some sort of local to global result for existence of walls. So it's really this sort of local to global idea that that was allowed by this geometry. Okay, well that's a good start. I said earlier the Coxeter groups are quite close in, Artin groups are generally quite close to Coxeter groups in spirit, so maybe we can try to use the same ideas to construct walls. So what about Artin groups? Can we essentially try to mimic this situation, this strategy here? So the bad news is that even though they have a presentation that looks really similar, Artin groups do not have a C prime 1/6 in the classical, so I'm going to say that, classical C prime 1/6 geometry at all. So here, okay, so they cannot, just because, for instance, they're not hyperbolic in general, and otherwise C prime 1/6 for a finitely generated group would imply Gromov hyperbolic. But in terms of the calligraph, you can also see it directly. So here's an example for, even just for a dihedral Artin group on 2 generator with MAB equals 4. So inside the calligraph, you're going to see Euclidean planes. Just going to draw a tiny portion. Where we've got A, B, A, B, 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 etc. A, B, A, etc. So these cells represent the standard relation ABAB equals BABA, which is my relation for MAB equals 4. But you see that they kind of pile up. So here's one cell. Here's another cell. But now they intersect over a path ABA of length 3, which is kind of 3/8 of the whole length of the relation, which is too big for C prime 1/6. And it gets even worse when MAB gets bigger. Essentially, we have pieces, so these cells are going to overlap over almost 1/2 of the relation, which is really, really bad for any sort of small cancellation geometry. So we're very far from the original Coxeter situation. And so that's really due to the fact that now my generators are no longer order 2. So in the Coxeter case, my calligraph had unoriented edges, but now in the Artin case, the edges really have an orientation, and so that that creates less symmetry in the relation, which allows this sort of phenomenon to occur. Okay, so that's That's bad news. But there was an observation due to it's an observation of originally Apple and Choup. That even though there is no small cancellation in the classical sense, in, let's say, for G is the Artin group on this triangle 444 that we're interested in. So the cells don't have a nice sort of small overlap, but the Cayley subgraphs on just taking the dihedral subgroup, so on two generators AB or AC or BC, have a small overlap. The picture is going to look like the following. Actually, maybe I should. I'm gonna skip the picture. So essentially, what they're saying is that there's some sort of small cancellation geometry, but you need to take an infinite presentation instead of the standard finite presentation. And what is really happening here is that it fits the sort of cubical small cancellation framework of Y's, namely that we're going to be looking at the following presentation, but instead we're going to be taking as our new relators these Artin, the calligraphs of all these Artin subgraphs. And these are these kind of blocks that have a small overlaps and allow us to do some sort of small cancellation geometry. So what we'd like to do now is going to be some sort of combination theorem. We'd like, in the same way that Wise proved that the walls on the polygons extended to walls on the whole complex, what we would like to do is to construct first walls on these dihedral Artin groups and somehow extend them by a similar sort of local to global phenomenon to the whole calligraph and so to the whole Artin group. So thankfully, that second part, the local to global part, was done by a Wise. So there's a combination theorem due to Wise for cubical small cancellation. That is way too technical to state, but kind of the gist of it, or like the vibes of it, is the following. So if X is a cubical small cancellation presentation such that, so we should say C prime 1 over 14, such that the relators have a wall space structure, and some rather technical assumption. If we are people in the audience are very familiar with small cancellation, so it's this idea of generalized V6 condition plus other extra condition. Then the walls on the Ri extend to walls on the whole group, plus some control over the action. In particular, there are some additional conditions that allow you to deduce that the action is proper, etc. So that's the sort of that's the theorem that we want to use. And so the key thing to apply this theorem was kind of re-cubulating dihedral Artin groups. So we would like, what we would like is to be able to construct a wall space structure on our dihedral Artin groups, and we know that they don't have a nice small cancellation geometry, but still we can try to follow what Wise did. So the naive idea first is, again, try to same walls. So try to start from your piece, your cell, and construct these walls by going to the opposite edge, and try to extend and hope for the best. And actually it works, or partly. So these walls extend to the whole walls on the whole dihedral Artin group. So you're not going to have any self-intersection, even though you're very far from C prime 1/6. There's enough control. There's the combinatorial structure is rich enough that we can prove that the walls don't loop on themselves or do anything annoying. The problem is, so you're like, okay, we've got a wall, so now hopefully the action is proper. Problem is the action is not proper in general. Problem, the action on the dual is not proper. And the reason for this is I mentioned some examples of flats somewhere here, but there are some exotic flats where the walls actually look more like this. They all go in the same. They all go in the same direction. They might intersect a bit, but in particular, there's sort of a general direction of travel, and so it's quite similar to the second example I mentioned of z squared by just taking the vertical lines, where we obtain something that is not proper if you have something like this. So you don't have enough walls, and so what we had to do is, I'm not going to have time to describe these walls, but we had to construct new walls. I'm just going to say using the central direction of these groups. That's walls that are going to actually start looking in the transverse direction to allow us to get a proper action. So in the few seconds I have left, I'm just going to mention, I would say something about what happens, like there was a part 2 to the theorem, so not just what happens if we have all labels 8, at least 8, but allowing some labels that are equal to 2, so some commuting relations in our presentation. And this idea again kind of goes back to Apple and Choup, is going to be to do small cancellation over the right-angle Artin group by just keeping the two labels. So let's gamma be the graph with all labels MAB equals 2 or at least 8, and there are no subgraphs of this form, 2, 2, 2, 2, then A gamma is properly cubulated. And the idea here is going to be similar to what we did before, but instead of doing cubical small cancellation over a free group, it's going to be cubical small cancellation.
Can you read the board?
Oops, sorry. It's going to be cubical small cancellation over a rag. The rag corresponding to just keeping the two relations. So doing this sort of cubical small cancellation over a rag, this idea appeared in Wise as well. It was used by Arshanseva and Hagen for questions related to asymmetrical cylindricity, by Macarena Arenas for questions related to sphericity. And so doing kind of cubical small cancellation over a right-angled Artin group using these ideas allow us to cubulate quite a lot of new Artin groups, including Artin groups that have cohomological dimension arbitrary large. And I think I'm going to stop here. Thank you.
Do you have questions?
What goes wrong with the square? Is it
Right. So what goes wrong with the square? So I said that in the original case the calligraphs intersect kind of nicely. But let's say, for instance, you have if you have let's say you have your dihedral Artin subgroup, and in your graph you say maybe I should have been a bit more careful. When I say no square 2, 2, 2, 2, I can have some labels here that are not 2. So if you have say a dihedral 8, and you have an element that commutes with both elements, so you're going to see your calligraph of AAB, but if you translate by that element, you're going to have a parallel copy. Okay, so this is C times the calligraph of AAB. And from the point of view of cubical small cancellation, even though these copies are disjoint, they have kind of big coarse overlap. You get like infinite grids between them, and that was mentioned in the Kashia's talk last week on cubical small cancellation. So this is bad from the point of view of small cancellation, which means that instead of taking our new relators to be just the calligraph of the dihedral Artin group, we're going to have to take our new relators to be not just this, but essentially the calligraph of normalizer of this dihedral Artin group. But the problem is that if you have two dihedrals that commute, you need those normalizer to be the same. Otherwise, you might create some large overlaps again in a similar way. And that's where, at least if you don't have squares 2, 2, 2, 2 like this, you don't have any pair of dihedral that commute, so you're sure to remove this problem. Kind of the more general condition, which is maybe harder to see on the graph immediately if you're familiar, is that if you have two commuting dihedral subgroups, you need the normalizers to be the same.
More questions?
Do you know when your examples are Cauchy special?
Not yet. Yes, that would be the next step. That would be really nice. So virtually special is quite hard in general because you need in particular to construct a finite index subgroup that acts specially. But even for these arting groups in general, we don't even know. We don't know that they're residually finite. We know that there are some finite index subgroups because you have a morphism to Z, you have a morphism to the Hoekstra group, but it's not clear that any of the finite index subgroups that you can construct in this way might be enough to get a special action. That would be a really nice next thing to look at.
More questions? So let's thank Alex again.